Hello. I'm Professor Laura Dalton. I'm an assistant professor at Duke University in the Department of Civil and Environmental Engineering. I've been there since August 2022. Went straight in from a PhD straight into a faculty position. And it's been quite a journey.
Oh, yeah. I'm Ivanka. I'm a high school student who's really passionate about climate and sustainability. And I first got really interested in methane emissions when I did my research project at the University of Minnesota under a USDA scientist. And then I also did a project at Cornell, and they're both in reducing methane emissions from livestock. So I started this YouTube channel because I wanted to educate people about methane emissions and mitigation strategies. And I also wrote this book about methane emissions that goes more into detail than my videos.
That's fantastic.
Thanks.
Yeah.
And I'm really excited to have you on the podcast to talk about carbon dioxide, which is different.
Yeah, absolutely. Different, but still, they're both big problems. So,
Yeah. Okay. Do you want to share a little bit about your background and how you got started?
Sure. So my background is a little different than most. I actually started out in graphic design, and I have a degree in graphic design. Fun facts. Thought I wanted to be an architect, but then went straight into another undergraduate degree in civil and environmental engineering. Did it in 2.5 years, loved it, joined the concrete canoe team, and that really led to some other internships at a national lab. Which exposed me to X-ray computed tomography, which is what I use to study pretty much everything I do now. Did a master's, went back to the national lab, and decided to do a PhD, just not on what my master's was in. So kind of a little all over the place, but.
Yeah. How did you land in the climate space? Like, what motivated you to join?
Yeah, so my first research project was on foamed cement, which was it's what's used to stabilize wellbores out in the Gulf of Mexico, so on and offshore wellbores. So there was a big oil spill in 2011, and originally they thought it was because of this foamed cement that didn't set correctly. Turns out, I think it was actually a few different problems, but it led to a huge oil spill, and that was the first research project I was working on. Which then led into me having a research project with the Department of Energy doing carbon capture and storage in sandstones. So we're actually able to replicate the conditions in the subsurface, so high temperatures and high pressures, and then actually visualize what's happening as we're storing CO2 in rocks. So that's the experimental work I was doing at the National Lab, which was it's a little bit of visual, creative, but also analytical. So it really just combined my two passions. So yeah, it was
really cool.
Yeah, that was perfect.
Do you want to talk a little bit about the projects that you're doing right now?
Sure. So I have 5 PhD students. They are working. So I work a little bit, well, I should say broadly speaking, on carbon capture and storage, but that in the context of subsurface storage, so in like saline aquifers, also in cement-based materials. So Portland cement is a leading carbon emitter, and it accounts for about 8% of global carbon emissions. So basically, there's U.S. or China, the U.S., and then if you considered the Portland cement production as its own country, it would be the 3rd leading global emitter of CO2. Yes, it's mostly because of the scale at which we are producing it. We produce 4 billion tons of this material for the built environment annually, and there are reasons why it emits so much carbon. But it's a big problem. But we're trying to understand things like self-healing. So can concrete, just like how our own skin heals itself, can concrete be designed to heal itself, to reduce labor and also maintenance costs, as well as reducing more Portland cement that needs to be made to mitigate those CO2 emissions. So that's a big part of what we do. The other thing we're doing is you can use a lot of waste materials can be used as partial replacement for Portland cement. And mixture designs, not fully replace it, but we're looking at coal ash as a replacement for some Portland cement. So there's an abundance of coal ash just sitting in these unlined ponds all throughout the US. And we know that that can lead to some issues with leaching into the surrounding water and whatnot. And we're trying to see if we could reuse it and repurpose it in a way that it would be locked in the concrete. So that's another thing. And then 3D printing concrete underwater is a new one, which is really exciting. Yeah. And while this isn't really like climate focused, the one benefit here is that the project we're working on, we are only allowed to use at most 20% binder. So that's the Portland cement. And so by learning ways we can reduce the amount of Portland cement needed, we can mitigate the amount of emissions associated with our mixtures while still meeting performance metrics. So yeah, lots of exciting work. New, the 3D printing concrete underwater is a brand new project that I'm just really supporting a company who's leading it, but learning a lot. Yeah.
Wow.
Yeah.
Yeah. Can you go into more detail about the first point you talked about, like
Sure.
cement's healing properties?
Sealing. Yes. So so Roman concrete has been in the news a lot lately because there would be this excess calcium oxide supposedly in these mixture designs. And what that meant was then as concrete cracks, because concrete will crack, that's just a known fact, that's just what it does. But controlled cracking is fine, uncontrolled cracking is bad. Anyways, when it cracks, water can get into the microstructure. So concrete's porous, just like a sponge is porous, so it will absorb water. And so as that water ingresses into the concrete, like things like ions from chlorides, where depending on where it's located, and then also CO2 will actually make its way into the cement, but then react with that calcium oxide to form calcium carbonate, which can seal the cracks.
Okay.
In theory, right? It's not, by no means is it a perfect science, but there's been, and this isn't really new. We're trying to see how we can better understand this concept specifically for marine environments. So that's something one of my students is working on.
Okay.
Yeah.
Can you go into more detail about the other things you talked about too?
Yeah, of course. So for carbon storage in the subsurface, so my newest PhD student, that's why I hired her. I'm really excited to work with her and really carry on some of this work I was doing during my PhD. The big picture is, so I have my own X-ray computed tomography scanner. It's the only one of its kind in the US right now. I think some other people will be getting one soon, but we're very fortunate to have it. And so what it's designed to do is really fast scans, and we can design these enclosures to be able to do these high temperature, high pressure experiments inside the scanner. So we're not there yet, but we have the scanner, and she's starting to do some flow through experiments just to better understand reactive transport in porous media very broadly. So rocks are porous, specifically the ones we're storing CO2 in, right? The way I think about it is, right, we've extracted all this oil or petroleum for, right, energy. Okay, that's really what we've done for years. And what we need to do now is store all this excess CO2 that's down the atmosphere back underground where it was in the first place. And that really aligns with what the same issues that lead to all the carbon emissions with Portland cement. It's something that came from the earth, right? Subsurface. We've used it for something, all this excess CO2. We're just trying to put it back where it was originally. But that involves a lot of understanding of physics, mechanics, hydrology. Like, it is a super complex problem. And it takes a lot of time to understand what's going on and how to optimize is really how I think about it. So yeah, really excited. She's just starting, so haven't made too much progress, but we will.
Yeah, that's exciting.
Yeah.
So your expertise is all around these porous materials that capture CO2?
Yep. Or to store CO2.
So what does your team and lab look like?
Yeah, so the name of my lab is creative engineering. That's very much what drew me into engineering, was that it is a big level of creativity goes into at least what we do, which is a heavily experimental work.
Mm-hmm.
You have to do a lot of troubleshooting on the fly, and that just takes a certain level of ingenuity at times. But so my group, so like I mentioned, we have an X-ray CT scanner, which is a big deal. Not too many PIs, if any, have their own X-ray CT scanner. But we've also designed the lab in a way to do all of this really complex, high temperature, high pressure work. Additionally, I'm very committed to having a diverse group of individuals. I want people from all over the world to be adding, just everyone brings their own personal backgrounds, right? And their own lived experiences, which also helps really create a great learning environment. It can be challenging at times, of course, like communicating with anyone can be challenging, but I've just really enjoyed seeing my group of students just really mesh and yeah, just really progressing forward. But yeah, I have 2 students from China, one from Nepal, one from Brazil, and my newest students from the US. And then I had a postdoc who was from Israel, and then I have a visiting postdoc right now from Italy, and then I had a visiting postdoc last year who was visiting from the UK in Cambridge, but he is actually originally from China, but grew up in Singapore. So anyways, really from all over. And it forces you to really sit down, discuss, understand each other, right? And then from understanding, really just bringing all these new ideas to really propel and progress research.
Mm-hmm.
So
Yeah.
at least, yeah.
Yeah, that's a lot of different people from
Oh yeah. And they've all reached out to me. It's remarkable.
Wow.
Yeah.
So are you doing any projects in other countries?
So I am, that's a good question. Well, one, I did a Fulbright. I should have mentioned this. In the last year of my PhD, I was very fortunate to be awarded a Fulbright to do 9 months of research in Finland.
Ooh.
And while I was there, it was to learn about electrical capacitance tomography. So instead of X-rays, you're using electricity. Anyways, but still trying to continue some of that work. I haven't kept up as much as I would like to, but that is still a line of research I would like to continue doing. And then also with the scanner that I have in my lab, we're part of the Test Scan Collaborative Network. So that just means that basically anyone in this network, and it's mostly people from Europe who just have these systems just because that's where the company is out of Europe and Belgium. If they want to use my equipment for up to 5 days a year, they can, and then I could use their equipment. That's like this complementary experimental equipment, but nothing really ongoing right now, but some little things that might come through here soon, hopefully.
Okay.
So, yeah.
Yeah. Yeah, who else do you collaborate with? Do you collaborate with any like private companies or government departments or anything?
Yeah, no, that's another good question. So I'm actually an ORISE faculty. I have an ORISE faculty position.
Okay.
So what is that? Oak
Yeah.
Ridge Institute. Why am I always forgetting? Oak Ridge Institute of Science and Technology. Yeah, I think that's right. Yeah,
Okay.
or science and education. Sorry, ORISE. Yeah. And they are so it's a national lab out of Tennessee, but I've done their undergraduate program, their graduate program, and now I'm a faculty position as well. And so that's with other national labs throughout the US. So specifically, I work with the National Energy Technology Laboratory, which is where I did past research internships. So, but I still work very closely with them, and they had the carbon capture and storage initiatives. So that they're who taught me everything I know, is what I say. Great group of people.
Wow.
Other industry. So at least for the 3D printing concrete project, so that's government funded, but the company leading that is Mackay Ocean Engineering. And they're out of Hawaii, but they're an ocean engineering company. So
Okay.
working with them, yeah. And then I'm sure I'm forgetting someone. I don't know. I'm engaged in quite a few projects, so sometimes I forget
Yeah.
what all I'm working on, honestly. Yeah, that's all that's coming to mind at the moment.
Okay.
Yeah.
Yeah. And then, so you mentioned tomography. Can you explain like what that is first of all, and then how it works?
Yeah. Yes. So yes, X-ray microcomputed tomography. So or like X-ray CT. So if you've ever been to the doctor to have a CT scan of a bone or something like an MRI, it's a very similar concept. But at the doctor, you would have this X-ray source and detector spinning around you, right? You are stationary, it spins around you. Whereas what we're doing, it's much higher energy, much higher radiation to see through much denser materials, because specifically what we work with are rocks and concrete, so very dense. But so how it works is you have a stage in the middle, X-ray source detector, and your sample will rotate on a stage. And so basically you're getting a two-dimensional image at a bunch of different angles, like up to 360 degrees. And then you can take those images and reconstruct them into a three-dimensional representation of your sample. And we can go down to about 1 micron resolution. So that's very fine detail. Yeah.
Wow.
And also the scanner we have is very fast. So it can, in theory, go down to 5-second rotation scan, but there's always trade-offs with what you're trying to see, what resolution you can do. You can't just get all of that in one scan and expect it to be perfect. But the technology that that's part of this system is cutting edge, which is really exciting.
Yeah. Are you using any other technologies in your work?
For sure. So machine learning, AI. So we have these three-dimensional representations. The other part of what we do is exposing some type of sample to different conditions with time. And so that's kind of like a fourth dimension. So we have that three-dimensional representation, but then we can see how it changes with time.
Okay.
And so with that, we have permanent, digital representations of all of this. And so we can take that and really manipulate it however we want, right? You could do modeling, you can do various image analysis to understand what's going on. And then we really try to also share data sets with other people. That's a big part of tomography. I may have lost my train of thought. Oh, and AI. So, but a big issue is this scanner can do so many scans so quickly that honestly keeping up with the data analysis, it really requires AI. So my one student, her background's actually in computer science. And she has just hit the ground running, doing all kinds of work with deep neural networks and trying to see how we can process our data more efficiently and faster. If not, being able to do better predictive analysis as well. She's doing, so we're 3D printing some tiny plastic microstructures. So just if you think about zooming into a rock or a piece of coral, for example, it has this really detailed microstructure. And so 3D printing that and doing some type of mechanical loading while in the scanner, so you can actually see how it's deforming and then predict certain metrics or certain characteristics based on what we're observing. But anyways, she's just taken off. It's a skill set I do not have, but she's just done such great things. Yeah.
Do you guys use computer vision?
She has. Actually, that's something she's starting to do a little bit of. Since we have the scanner and we can see inside of materials, we aren't usually doing computer vision, but there is a reason that she's starting to look at computer vision. So, and she has done that in the past. And that's a big, it's a whole area in and of itself.
Yeah, is there anything else you want to share about your projects, like cool things?
I don't know. I'm sure I'm forgetting something. Oh, I'll at least mention the visiting postdoc from Italy. He is working on, so we have a lot of waste material from demolishing buildings, things like that. And a big issue there is how can we repurpose some of that material? And so what he's developed during his PhD, now he's a postdoc, is he's been looking at methods to remove cement from fine aggregate. So from waste, if you crush it down really fine, it's really difficult to separate that residual cement binder from these really fine aggregates. And he's developed a way to do that more efficiently. And we're testing that out in the scanner. We haven't made too much progress yet, but it seems pretty promising. So that's exciting to really see the progress being made, and just that it seems like it might work pretty well. So, but yeah, trying, repurpose, recycle wherever we can. Yeah.
Yeah, that's exciting.
Mhm.
So what kinds of challenges do you face in your work?
Challenges. So experimental work, I'll just say, right? Brand new technology, it's brand new. Things happen. Things don't always run smoothly or go as planned. It's just the process.
Yeah.
But yeah, I would say just being prepared for when something is down, right? And then just planning and not over promising can be a bit of a problem, a challenge. I think the other thing is just with PhD students, something I've learned again. Of course, I know myself as a PhD student, but every person's different. So then also just learning how to motivate different people, and managing different personalities. But other than that, it's really just supporting my students. But sometimes that comes with challenges, but just keeping an open two-way discussion is really the biggest part, right? We're all human. Things happen. And just, also realizing that you could do a PhD. It doesn't mean whatever you do will be groundbreaking, right? But it's important. It does matter. And I think that's another, I don't know, a certain amount of, I don't know how to say this, but like managing expectations of what a PhD is. It's usually a lot of hard work. And then, at the end, until you get to that end, it can just seem like, what have I been doing with my time? But it's a challenging process, but there's always a big reward at the end.
Yeah. Your work sounds really fun too.
I think so. But I guess actually back to what I was going to say, training students to be able to do this type of research takes time, right? Like I was just fortunate to have these amazing internships at a national lab that had 4 X-ray computed tomography scanners, and they were using them to study like these really complex geological processes. I've had one student come to my lab who actually had experience operating a CT scanner. Okay. And that's just something that you can't really expect a student to come in with that type of skill set. But it takes time, and that's totally normal. I always tell my students, when I was working at the national lab for 2 years in between my master's and PhD, it took me an entire year to finally get good data. And it was just 1 month after another of like, oh, it didn't work again. And then it finally did. And then I got all this data that I still use today because it's excellent data. It just took forever. So anyways, like perseverance, I think is a big part of any research and a lot of academic pursuit in general.
Yeah.
Yeah.
So what advice would you give to a high schooler or someone like me who would want to go into a field like this?
So I would say keep doing what you're doing. The fact that you even contacted me is great. Not being afraid to reach out and put yourself out there. Sure, some people might say no, but at the end of the day, most of us are pretty nice people. We're busy, but
Yeah.
just showing that you are so passionate and care about something that is so important in and of itself will set you apart from your peers, in my opinion. And yeah, the fact that you're already becoming engaged as a high schooler. I did not know what I wanted to do, hence the graphic design degree. So like if you are passionate about it and that's what you want to do, you can do it.
Thanks.
And you can make a difference.
Yeah.
Mm-hmm.
Yeah, I would love to join your lab if I went to Duke.
Hey, let me know.
Yeah. I think that's all.
We can always use the help.
Yeah.
Always looking for help. Yeah. Yeah.
Mm-hmm. Yeah, it was really great talking to you. I learned so much.
Yeah, of course. Happy to do it. I appreciate you putting in all this effort to even do something like this.
Thanks.
Yeah.